Hello, hello. I request everyone to come inside and take their respective seats. See, I am not visible here. The camera is towards you, right? I can see you. Hello, hello, hello. Everyone, please, I request all the students to come inside. It's fine. হয়ে গেছে তো? Should I get down? কি করব? এখান থেকে তো আওয়াজ বাইরে যায় না, অ্যানাউন্স করলেও শুনতে পাবো। Everyone please come inside. I request everyone to come inside the hall. I request all the students to come inside the hall and please take their respective seats. শুনতে পাবেন, জাগিয়ে বল।
Hello. 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 এমনি বলে তো শোনা যাবে। Hello. Hello. Hello.
হ্যালো,
আপনারা শুনতে পাচ্ছেন?
হ্যালো, হ্যাঁ
আপনার শোনা যাচ্ছে?
হ্যাঁ, শুনতে পাচ্ছি।
আচ্ছা, ওকে।
Very good morning, everyone, all the teachers, alumni, students, and our guests. So today is the third day and the concluding day of this symposium. So in the morning we have 4 lectures, 2 will be in virtual mode and the 2 that will be in physical mode from here. So the first 2 lectures are in online mode. So I would like to request Dr. Jayant Bandyopadhyay to take over the chair for this session. And Sohini, please hand over a flower bouquet to Dr. Bandyopadhyay. Sir, if you count number of photographs, whatever is taken in this symposium, then he will be far ahead of us. So I am handing over this session to Jayant.
Good morning, everybody. Thank you very much that you could make your time getting up from the bed and coming here today. Today is a very exciting day. There are very important topics that we will be discussing. And some of the things that you will hear today, we have some of the people they are actually implementing in the industry. So you'll see theoretical to actual industrial implementation. You'll see that one. We'll have a lot of question and answer. With that, I am giving it to Obro. Obro did his MTech and PhD here. He was with Reliance last time I checked, but this morning I got the update of you have joined Aditya Birla Technology Group. Whatever you are doing, I don't know how much you can share. Please enlighten with your talk. Waste remediation, one of the things that we don't see it here, but the countries like Brazil, they take the water, but when they dispose the water, it's better than what they take as intake. So this is one of the important topics that is coming worldwide. So Abra, we are leaving it to you. Give us all your findings and insights. Anything else? So let us listen, then we'll have some questions. Okay?
Share your slide.
Yeah.
Share your slide.
So I have a video of some I'm
Okay, it is okay.
Is my presentation?
Yes, it is visible.
So good morning. As we know, the carbon neutrality is the current hot topic because all of us are facing issues with CO2 emission and greenhouse gases, and that's why so remediation is required, and the scientific community is working on that by different ways, uh, using renewable energy or by capturing conversion and utilization of CO2, and some eco is coming. Hello. So my today's topic is to uh, remediation of wastewater by producing hydrogen, which wastewater contain the ammonia or urea. So different sources of hydrogen are water, hydrocarbons, biomass, ammonia or urea. So from water we can produce hydrogen by either electrochemical splitting or thermal splitting, by uh, coke or coal gasification, and from hydrocarbon there are different routes for production of hydrogen like steam methane reforming or others, and from biomass there are biomass gasification, which can produce hydrogen from the biomass, and from urea or ammonia we can do electrolysis for producing of hydrogen. So hydrogen is the cleanest fuel, as we know that it can produce only water when combustion is occurred. So what is the advantage of this process? This process has twofold advantage, like remediation of wastewater, that is wastewater that contain urea or ammonia that can be removed from the wastewater, so that will be treated, and that will be reused or recycled to the mainstream. And another is the added on, we can get the hydrogen, which is the cleanest fuel. So what are the different sources of ammonia or urea containing wastewater? That may be public urinals or urea ammonia plants or fertilizer plants. So from where we can get the concentration of urea, which varies from 0.3 to 1.58%, and in that ammonia varies from 17 ppm to 9%. So we can electrolytically produce the hydrogen from this type of wastewater, because this type of wastewater requires some treatment before disposing of to environment, as the environment protection rule of 1986, it requires to be less than 50 ppm in the wastewater. So we need to reduce the concentration of the urea or ammonia to the permissible limit. So at present, the hydrogen is produced from the alkaline or acidic water electrolyzer that uses the ultra pure water, that is deionized water, which doesn't contain the other ions, because that ions may interfere the production of hydrogen, and may corrode the electrode and affect the electrolysis process. And as the pure water doesn't have much significant conductivity, so some supporting electrolyte is required to increase the conductivity of the electrolyzer, and normally 30 to 20 to 30% aqueous KOH solution is being used as the supporting electrolyte. And for splitting the water, standard cell potential required is 1.3 volt. So in the case of ammonia or urea, we found that from the literature, the standard potential is required is 0.06 for ammonia, which is 95% lower than the water electrolysis potential, and for urea that is 0.37 volt only, that is 70% lower than the water electrolysis potential. So And in this case, the electrolyte could be the wastewater, which can be found in the different industrial wastewater or in the public urinals. So that can be utilized for treating and producing hydrogen. In that aspect, we found some literature which are benchmark up to the date, and these are using the mainly the costly catalyst, that is ruthenium, platinum, iridium based, or either platinum based. And in this case, you can see that the supporting electrolyte contains the more concentration compared to the base, the desired base compared to the ammonia concentration. So we are spending more supporting electrolyte compared to the ammonia concentration. So we are trying to find out if we can do the electrolysis with some less concentration of KOH as a supporting electrolyte, and using some low cost electrode which is readily available or can be used for long time. And in this case, in these two cases, the current efficiency reported in the first case is 92%, which is quite low, and they didn't reported the energy efficiency. But in the second case, the rotating disc electrode has been used, where the hydrogen and nitrogen produced in this process was mixed up, and not pure hydrogen was being collected in this process. And the current efficiency reported is from 95% to 99%, and the energy efficiency reported is around 45%. So we tried to improve the energy efficiency and current efficiency with low cost electrode and some dilute supporting electrolyte. The experimental setup consists of a electrolytic cell that consists of two electrode, cathode and anode, divided by a rectangular conduit. There was a provision for inserting the ion exchange membrane, but in this case we didn't use ion exchange membrane for this experimentation. And the produced gases were collected in the aspirator bottles connected to the each cells, and the volume displaced water was collected, and the volume of the gas sample was measured. The voltmeter and ammeter was connected to the computer, which was through the data logger system. So we monitor and monitored the current and voltage in the computer and calculated the current and energy efficiency accordingly. These are the different electrodes used in this experiment. First is a flat plate electrode, and in the second we can see that the packed bed electrode are used, as shown in the D. It is the hollow cylindrical cage made of some insulating material, which was filled with some packing material. One type is solid cylindrical material, another is hollow cylindrical material. We found in case of hollow cylindrical material some gas entrapment was there, so we discarded this and we carried the experiment with solid cylindrical packing electrode material. So experiment was conducted at the ambient condition, that is at the room temperature and atmospheric pressure. As in the Kolkata, the room temperature varies from 24 to 37 degrees centigrade during winter and summer. So the average fluctuation was there around 8 degrees centigrade, and we calculated the standard deviation for that, and we found it is plus minus 2% of standard deviation, which is within the range of the acceptable limit. So we we did the experiment in different ammonia concentration with a 0.5% KOH solution as a supporting electrolyte and at the 3 volt applied. The current efficiency is the ratio of the current required by theoretically required by the actual current consumed. So it is calculated in that way, and for the energy efficiency similarly the theoretical energy required to the actual energy consumed is the current efficiency. So in this case, we can see that the current or energy efficiency in the first hour it is lower. Around in case of current efficiency, it is varies from around 52% to around 70%, and from the second hour onwards, the current efficiency reaches almost the steady state. It is being suggested that the current efficiency has been found very low in the initial stage because due to the dissolution of the hydrogen produced in the electrolyzer to the electrolyte, so it reaches the saturation concentration of the hydrogen and then collected at the aspirator bottle. So at that time we couldn't get the hydrogen collected in the aspirator bottle, so the current efficiency has been found to be low in this hour. And it was calculated theoretically, but due to some experimental setup constant, we cannot do the experimental validation of this consideration. Similarly, energy efficiency increases from around 25% to 35% at the initial, and then later on it reaches the steady state around 48%. This is the effect of the applied voltage on the current and energy efficiency. In current efficiency, there is hardly any effect on the current efficiency by the applied voltage. But in case of energy efficiency, as the energy is the multiplication of the current and potential with time, so as the potential increases, the energy efficiency decreases. So it has effect on the energy efficiency, but not in the current efficiency we found. So if we compare our experimental data with the base case 1 and base case 2, we can found that we operated the electrolyzer with ammonia concentration from 0.2 to 1%, where the ammonia concentration was in the range of those experimentally reported in the literature. And as a supporting electrolyte, we use the dilute KOH solution, which is very low compared to the literature reported in the literature. And we also use the low cost stainless steel 316 electrode. In case of literature, they have used costly platinum electrode, and we have used the packed electrode, which has given the current efficiency of around 99.6% at the steady state, and the energy efficiency has been calculated as 48%, which is slightly higher compared to the reported value of 45%. So in case of urea, there is hardly any literature on urea electrolysis, so it is the noble, you can say, the noble method for urea electrolysis to produce hydrogen. And in case of current efficiency, we did the experiment with urea solution from 0.75% to 2.5%, and similarly we calculated the energy efficiency as well, and we found that the current efficiency reaches almost 95% to 98% in case of urea electrolysis, and the energy efficiency reaches almost 46% in the case of urea electrolysis. So this is the result of our experimental data. The source of hydrogen used, as I mentioned, it is 0.75% to 2% urea solution, and the supporting electrolyte similar to ammonia electrolysis, it was optimized at 0.5% KOH solution, and same electrode was used as SS316 is the electrode material, and same geometry of the electrode also used as used in the ammonia electrolysis as well. In this case, current efficiency has been found to be quite low compared to the 99.6% in the ammonia electrolysis. And the reason we found that could be due to some electrochemical dissolution of electrode and some recombination reaction either in form of electrochemical or non-electrochemical, and deposition of the electrode material, that is maybe iron from the anode to cathode, and we then did the surface analysis by FECEM, and these images are first row is the fresh electrode material which has no some deposition or corrosion at the surface, and it is showing the smooth. And in the second case, we take the picture of anode material after use, and we found that some corrosion and oxidation also occurred at the surface. And in the third row, we found that these are the images of cathode material after electrolysis, and so we found that some iron deposition was occurred at the surface of the electrode cathode. And we also did the XRD analysis of those cathode, and we found that there is some oxide, and in the anode similarly these oxides are present after the electrolysis of ammonia or urea. And we also analyzed the electrolyte before and after doing the electrolysis experiment, and in the AASS result it could be found that in case of ammonia the electrolyte contains 0 before the electrolysis, and after it was 0.13 ppm, while in case of urea that is 0.15 ppm. So dissolution of iron was occurring from the anode and deposition at the cathode as seen in the efficient images. So in the conclusion, in the acidic solution as a supporting electrolyte in case of urea was experimentally conducted, but there was some rapid corrosion of the electrode and could not further perform. So in case of ammonia electrolysis, the current efficiency has been found to be 99.6%, and energy efficiency is around 48%. Those are higher compared to the literature reported values. And in case of urea electrolysis, current efficiency and energy efficiency are 98% and 46%, and those could be higher if we combat the corrosion of the electrode and the other electrochemical side reactions which are reducing the current efficiency from 100% to 98 or so. So energy efficiencies obtained in this, as I mentioned, are higher compared to the literature values, and XRD and FECM analysis already shown in the figures are it proves that the oxidation of iron occurs at the surface of the electrode, and dissolution of iron was confirmed by the AASS analysis, and dissolution and oxidation are the mainly responsible for not attaining the current efficiency of 100%, as I mentioned earlier, and higher surface area compared to the flat plate or rotating disc electrode. And in case of rotating disc electrode, there may be chance of recombination of the product gases to form the ammonia or other product. So there could be the reason which is lowering the current efficiency or not attaining the current efficiency of 100%. So in our case, that actually was avoided by H-type, using H-type cell and the packed bed electrode. Thank you.
Thank you very much, Abro, for a nice presentation. I have some quick questions or my clarification. I think you should define how you are defining energy efficiency and the current efficiency in the beginning, so that people will know. And what you listed at the last item, is it due to the surface area increase that you are getting this better
You are
efficiency?
on mute, Chandana.
Mute? এখানে একটা মাইক্রোফোন আছে, এটাকে আনমিউট করতে হলে টাচ হলে হবে? ওকে। অপ্র, can you hear me?
You still, I can't hear.
Okay. এখন?
Yeah.
তাহলে এটা লাগবে। এখন শুনতে পাচ্ছ? Is it okay?
Yes.
Okay. One of the suggestion, you have defined energy efficiency and the current efficiency. You should define that from the beginning, like how do you define those terms so that audience can understand. That is one thing. And what you have shown, the flat electrode and the rotating disc versus this pack bed, is it due to the surface area more that is causing this better efficiency?
Yes.
And one of the things that you have is corrosion, that it is corroding the electrode and all. How long it is running, like compared to the platinum? Do you have that? I think that will be an interesting thing. In addition to this, what you have done, I'll tell you for the rest of the audience, you know hydrogen economy, the fuel cell is coming down, EV battery, EV, if you see the life cycle is not complete, like 20 years from now, you'll see lot of waste material is coming. So hydrogen is a good source of energy. Hydrogen problem is the hydrogen management, like the storage and transport. Ammonia is considered to be one of the things that you convert to ammonia and bring it somewhere, and then split the ammonia again. So this what may be very interesting for the future studies, because platinum and stainless steel, it is like a factor of 5 cost effort. So if you can do that too, I think that will be very good result for the future. With that, that is my question. Okay. Any question from the audience?
Yes, I have some questions. Will you allow?
Yes. Online.
Yes, I am online.
Okay. We can see you in the video if you want.
Video that I don't know why video is not being on. I don't know.
We want to see your beautiful face.
Anyway, that I do not know why video is not coming.
Okay, go ahead. Ask your question. Ask your question.
First of all, that you said that your electrode is a stainless steel electrode, and that also pack bed. How come the pack bed can be electrode? That is one question. And second thing is that you said that iron is oxidized because it is coming to this solution. So then, what is that oxidizing atmosphere is there? Because your hydrogen is being produced. So atmosphere is basically reduction atmosphere. Then how iron will oxidize to dissolve with the solution? These are the two questions.
Obro, you want to answer?
Yeah. For the first question, packed bed electrode has been used because I have shown that the figure. I can show again.
Now my question is not that pack bed, why it is used. I say how electrode can be a pack bed.
Yeah, so like porous material, it is something packing, and the electrode current connector was inserted in that pack bed. So it was the vertical configuration was like this. And to increase the surface area, we use that package instead of porous material.
Is that answer your question, Kartik?
No, no, no. See,
I think why don't we do one thing, Kartik? Let us have this one offline. We can have a separate discussion. Partha is also
okay,
here.
okay, let us, okay, then what about the second question?
A second question is that's what his last point was exactly that one. The surface area.
The environment is alkaline. In that alkaline environment, the occurs.
Alkaline atmosphere.
Yeah, because the alkaline
And how hydrogen is being produced there? Because solution, this iron is being dissolving in the solution. We are getting the iron in the solution.
yes.
And then how you say that it is in a alkaline atmosphere? What about the hydrogen presence there? There is no role of hydrogen there then?
Okay, very good.
No, it is a side reaction in which the iron is getting dissolution from the anode, and with reaction in the alkaline medium, the supporting electrolyte was the KV solution. So the iron gets oxidized and hydrogen was produced at the cathode, and the cell was undivided. So nothing was anodide or cathodide separated. So
But that is not desirable. Okay, anyway, if it is so, it is not desirable. Have you thought about it? How to protect it? How to resist it?
yeah, in later on we used some iron selective membrane to combat that diffusion and
I think Kartik, I'll interrupt for a second.
Okay, then thank you.
Yeah, we will have this discussion. Maybe it is much better elaborate discussion. There is a question online. Aubrey, can you see the questions? Question is, are you using any salt bridge in your experimentation? See the chat box?
Now you can see me.
Beautiful. You look like Dada Sai Phalke, huh?
no,
Are you-
what is was used because it was the H-type cell and that was undivided and no liquid was used in between the anode and cathode. And as a supporting electrolyte, KV solution was used.
Is that okay? Any questions from? I think we have a question here.
Yeah. On for
Is it on? এখানে There is one more question for online audience.
Hello, sir. My name is Arvind Dashgupta. So I want to ask one thing. Like this setup, can it be used in sewage treatment plants? Like you were saying that for human urinals this can be used. So if it is scaled up, can it be used in sewage treatment plant, or does there needs to be some other modifications or something like that?
Could you hear the question?
And there is a similar setup that is electro-oxidation process occurs and electropropulsion and electrocoagulation. Those are similar setup but some different processes are there. And this is used normally for where the wastewater content urea or ammonia solution in a solution.
Hey, Obro, I suggest that you give our regular the talk on one of the next talk will be Biswajit. You add Obro this topic. I think that is a lot of questions will be clarified in our this bi-weekly meeting. You know, this
Yes.
Obro clarify few things on that one. I think that will be a good presentation. A lot of people will be interested. Okay. With that, I think I'll. we would like to thank you, Abba, for giving your time and presenting this one. Next topics, Karthik, it will be Padma. We do not have any of the resume. I think they are the research scholar. Can you say some words about them and then we can start? Padma will be presenting or? Okay. Karthik, can you hear us? I think, Karthik, your mic is off, your audio. You put the audio on for a second, talk and then put it mute.
For second talk, my student is there.
Yeah, can you introduce her? She is a research scholar who is here and all this, working jointly with him.
Actually, that she can introduce herself itself. Padma, you please introduce yourself.
Okay.
Sir, good morning, sir. Am I audible?
Yes.
Sir, good morning, sir. I am Padma, working as assistant professor in Gayatri Vidya Parishad College of Engineering, Vishakhapatnam. I am doing my PhD under the guidance of Shushmita Datta Madam and Karthik Chandra Ghanta, sir. I have joined my PhD and in the year 2016, sir. And I am working on bio-removal of heavy metals from the industrial wastewater using microorganisms.
Okay, Padma, just before you start, one thing is that please make sure it is finished by.
She is already employed, so she is working as a professional scholar.
Okay. Now you have 15 minutes, then we'll have discussion. A lot of questions are coming. Please keep your timing. Okay.
Okay, sir. Sir, shall I share my screen?
Yeah.
Sir, my screen is visible, sir? Sir? Can I start my presentation? So, good morning, everyone. Today I will be talking on the topic bio-removal of multiple heavy metals using isolated bacterial strains from contaminated water. So, as we are well aware that due to increase in industrialization, the water which is being used by the industries is let into the environment. So the water which is coming out of the industry is having highly toxic chemicals like heavy metals, inorganic, organic chemicals. And if that type of water coming out of industry is being mixed with the environmental fresh water, then it will cause harm to the organisms or the aquatic living organisms which are present in the water. So here in the figure you can see that the yellow arrow marks are being the heavy metals which are being mixed with the fresh water. So we should treat the water from the industry before we let into the environment. Otherwise, like totally 53 metal ions were identified as heavy metals, and if these metal ions will get in contact with the living cells at high concentrations, will lead toxic effect to the living organisms. So these heavy metals are being categorized into three categories: average toxic and high toxic. Low toxic molybdenum manganese, under average toxic zinc, nickel, copper, vanadium, cobalt, tungsten, chromium, and under high toxic we have arsenic, silver, antimony, cadmium, mercury, lead and uranium. In the group of heavy metals, present my work is on nickel, chromium and lead. I have selected these three heavy metals. So if we see the permissible limits of nickel, that is 0.02 mg per liter, lead 0.01 mg per liter and total chromium 0.05 mg per liter, and according to the Environmental Protection Act. So to remove these heavy metals from the industrial wastewater, after the processes, we have different conventional methods like precipitation, reverse osmosis, ion exchange and adsorption. but we are being using these methods in many of the industries to treat the wastewater. But there are some disadvantages in using these methods like precipitation. If we use any chemicals to precipitate the toxic chemicals, these are not specific to any chemicals. Like it will remove all the chemicals from the wastewater, and it is very ineffective in removing metal ions at very low concentration. So though we use precipitation, low concentration heavy metals cannot be removed in this method. In reverse osmosis ion exchange, these methods are very expensive. Adsorption, again desorption studies are required. So in present emerging techniques, we have two new methods: phytoremediation, where we will be using algae to remove the heavy metals from the wastewater. But the disadvantage is the algae process is very slow. And bioremediation, here we are using bacteria, live bacteria, which can remove the microorganisms from the wastewater. So this is very economical, and the bacteria growth is very rapid. There is a rapid growth of bacteria. So due to the growth of bacteria is very fast, the process is also very quick in removing the metal ion, and it is very specific. Plus low concentration heavy metals can also be removed using bacteria. But here also we will get sludge generation, but this sludge which is being generated can be biodegraded. So mechanism using like we have four different mechanisms: bioadsorption, bioaccumulation, bioleaching, and bioprecipitation. So in my present work, what I am trying to do is to like bacteria will be feeding on the toxic heavy metals like chromium, lead, nickel, and they will be converted into non-toxic end products. So the bacteria will be consuming this as nutrients, and it will be leaving non-toxic end products. For example, chromium 6 is toxic form, but the bacteria is consuming chromium 6 and it is giving out chromium 3, which is non-toxic form. And whereas lead and nickel, it is not giving out any lead and nickel after the nutrients are being consumed. So in the previous literature, there are works done on different types of bacteria to remove the heavy metals, like Bacillus ceres. This bacteria can remove chromium 6 and lead at initial concentration of 100 mg per liter, around 75% of removal. Whereas Bacillus cereus can remove nickel, initial concentration is 5 mg per liter, removal percentage is 52.7. Pseudomonas can remove lead too. Initial concentration is 50 mg per liter, percentage removal is 90. Pantonia agglomerus, this organism can remove chromium 6 at initial concentration of 100, percentage removal is 83.64. But what I am trying to do in my work is like I am trying to like use one bacteria to remove multiple heavy metals. Like one bacteria is being used to remove chromium, nickel, and lead at a time, and the bacteria which is being isolated is not from specific contaminated site. The bacteria which is isolated is from a common effluent treatment plant, where it gets wastewater from a small scale industries nearby. So my objectives of are isolation and screening of metal resistant bacteria, determination of minimum inhibitory concentration, biochemical characterization of bacterial isolates, removal of heavy metals from water using isolated strains. So I have collected contaminated water from a common effluent treatment plant, which receives wastewater from around 80 industries nearby. and it treats those wastewater, and that treated wastewater is being allowed to the environmental freshwater bodies. So this effluent has all types of toxic chemicals in it. It has all types of heavy metals in it. So, assuming that the bacteria which is isolated from such contaminated place will have resistance to multiple heavy metals, like I have isolated these bacteria, and after isolation, I have carried out minimum inhibitory concentration. Like, what is the minimum concentration till which that bacteria can be resistant to that heavy metal? So once the bacteria can grow in that specific heavy metal, that bacteria is selected as as a strain which can remove the heavy metal from the wastewater, and that's isolated bacteria is being like biochemically characterized to identify what bacteria it is, what is the specific bacterial species. And after identification of bacteria, I have conducted I have inoculated this water in synthetic wastewater, which is having lead, nickel, and chromium separately. And I have conducted experiment for 24 hours, and I have tested what is the initial concentration and what is the final concentration, which gives the removal percentage of that specific heavy metal from the synthetic wastewater using that bacteria. So these are the three bacterias which I have, like, actually I have isolated nine bacterial strains, and those nine bacterial strains I have grown in different agar plates which were inoculated with these heavy metals separately, nickel, lead, and chromium. And in those nine bacterial strains, I have found that these bacterial strains were growing efficiently, faster, with less time, and the growth was seen prominent. So I have selected these three bacteria and conducted the further experiments. So these are the results of minimum inhibitory concentration. So here the first graph shows that the S1, S2, S3 are the three bacterial strains which were inoculated on the lead contaminated wastewater, and I have seen that the number of colonies being observed at were till like number of colonies were observed till the 1000 mg per liter for lead S1 bacteria. S1 and S2 bacteria can grow till 1000 mg per liter in 24 hours. And after still I increased the concentration, there was no growth seen. Prominent growth was not seen. So we can fix the minimum inhibitory concentration as 1000 mg per liter for S1 and S2. And for similarly, I have conducted the experiment for nickel. For nickel, it growth was seen till 250 mg per liter. 250 mg per liter, and for chromium the growth was seen till 250 mg per liter, S1 and S2. But there was like very little growth seen at S3, and S3 we can have at 150 mg per liter. S3 was growing till 150 mg per liter. S1 and S2 are showing the similar results. So these are the characterization morphological characteristics. Like S1 is circular diffused, medium and small, opacity is translucent, texture is glossy, and the color of the bacteria is white, morphology is smooth, and this is gram stain is positive. So S1 and S2 are gram positive bacteria, and S3 is gram negative bacteria. Colony color of S3 is little greenish. It is texture is glossy, opacity is opaque, and colony size large, and shape is flat. And these are the biochemical tests: indole test, catalase test, methyl red, citrate, and oxidase. So these are like S1 is negative for indole test, positive for catalase test, methyl red test it is negative, citrate test it is negative, oxidase test positive. SO2, S2 is indole test negative, ketyls test negative, methyl rate test negative, citrate test negative, all like oxidase test is negative. And here the utilization of carbohydrate, how the different types of carbohydrates are being utilized by these three different bacteria. So here we can observe that sucrose is being like consumed by S1 and S2 bacteria. Lactose was not consumed by any of these three bacteria, and glucose was consumed only by S3 bacteria. Like maltose was consumed by S1 and S3 bacteria, and xylose was also not consumed by any of these three bacteria. So it, like, we have identified by these biochemical characterization that the S1 may be Staphylococcus species, S2 Lactobacillus, S3 Pseudomonas species. Next, I have conducted the experiment, like I have inoculated these bacteria with the initial concentration of 50 mg per liter of chromium 6, and after 24 hours of incubation period at 30 degrees centigrade, I have seen that S1 and S2 almost 100% removal is being there, but S3 it only 30% removal, means 50 mg per liter concentration, initial concentration, S3 could remove only 30%, whereas S1 and S2 could remove complete 50 mg per liter from the synthetic wastewater. Similarly, for lead 2, like 50 mg per liter is inoculated for 24 hours for at 30 degrees centigrade. So S1 is could remove only 15%, S2 could remove 32.5%, and S3 could remove around 27%. So this is the amount of removal of lead 2 by X1, S2, S3 bacteria. But I have observed that though the bacteria are growing in nickel plates, but it could not remove in the liquid medium. When I have inoculated these three bacteria separately in nickel inoculated synthetic wastewater, I have observed that initial and final concentration after 24 hours of incubation period, there is no degradation of nickel. 50 mg per liter was bacteria could not remove. Though the bacteria is having resistant to nickel, but it is not having any removal properties for the nickel. So I finally conclude that the three bacterial strains have high resistance to heavy metals like lead, chromium, and nickel, which were isolated from industrial contaminated wastewater. And the cultural, morphological, and biochemical characteristics of these three strains were provisionally accepted as Staphylococcus, Lactobacillus, and Pseudomonas species. The growth of isolated bacterial strains S1 and S2 were observed till 1000 mg per liter for lead and 200 mg per liter for nickel, and chromium 6 in 24 hours at 35 degrees centigrade. The growth of S3 was observed till 700 mg per liter and of lead, and 100 mg per liter for nickel and chromium for 24 hours at 35 degrees centigrade. All the experiments were conducted at neutral pH, and the strains were found to remove chromium 6 and lead, but there were no removal was observed for nickel. Further, I have to do EDEX analysis of the bacteria before and after treatment, which shows that the bacteria, if the bacteria after the treatment with these metal ions, if the bacteria is consuming, then EDX analysis will show that bacteria are these heavy metals are present on the bacteria. And similarly, FTIR analysis has to be done. And finally, I have to optimize the variables like heavy metal concentration, pH, time, and inoculum volume for the maximum removal in minimum time using one factor at a time method or any other optimization techniques. So till now we have observed that there are number of works which are being carried out for the removal of heavy metals using bacteria, but these works were till lab scale, but we have to increase it for the large scale, in a large scale process where we can use this live bacteria for the better treatment of industrial wastewater with less usage of chemicals. These are the references. Thank you, sir.
Okay, so it's a very good presentation. Just for understanding, what is happening to the bacteria after it consumes all the metals? Is it increasing by mass also, and how long it is taking to double the size or volume?
Sir, number of bacteria, like it is increasing. The population of bacteria is increasing, sir.
Okay, so can it be used as a autocatalytic reaction? Like you can have that same bacteria, it will generate automatically and remove more and more metal, or you have to discard that one.
Sir, like here, what is happening is bacteria is consuming it as a nutrient, so the high concentration metal is being dispersed in bacteria.
Okay,
So this can be used.
okay, and I do not know anything about the bacteria, but the lactobacillus, that is the same thing you use in the yogurt and dahi, right?
Sir?
The
Sir,
lactobacillus.
sir, bacteria is available in everywhere, sir, in air or water or soil, everywhere, but the species are different, sir. Lactobacillus, we have to find out the correct species which is being isolated
Okay.
from that contaminated wastewater, and we cannot use for making dahi or so. This bacteria cannot be used.
Okay, okay. One just a comment. What you showed as a Chrome 6 to Chrome 3 for the audience here and the online. There is a process for making propane to propylene or isobutylene to isobutylene called Hood process or CATOFIN. There the environmental regulation is coming because Chrome 3 is a carcinogen, Chrome 6 is a carcinogenic, meaning it causes cancer. So if you have some solution like this, that where it can reduce this one Chrome 6 to Chrome 3, I think that process, Lamas, anybody from Lamas here in the audience? No. Okay. Oh, yeah, Lamas process is there. So this is very interesting, Padma. Carry on your work. Any question from the audience online? No question. There is a question online, I think. No. Padma, thank you for maintaining the time. That is very good. We'll have one more here. Any question? There is a question, Padma. Yeah, go ahead. Either here or
Yes, sir.
Hello. Like actually, I'm interested to know that whether we can use genetically modified bacteria, or is it better to use the natural species?
Sir, we can go for genetically modified bacteria, but at any place, naturally obtained bacteria will give good results than genetically modified bacteria. Because naturally, those bacteria has this capacity to take toxic chemicals as nutrients and give out non-toxic chemicals.
Okay. And is it also like economically viable than making a genetically modified bacteria, the naturally
Yes, sir,
occurring?
because this bacteria is isolated very easily. But
Okay.
making a genetically modified bacteria, we have a more tedious work. Like, and after genetically modifications, also we may get that result or we may not get.
Okay.
But here we are getting those results.
Thank you.
Okay, thank you very much, Padma.
Thank
And
you.
no more question here, right? Hey, you have a question. There is one more question. One more question. Just one sec, Padma.
Yes, sir, yes.
I have a question that can you hear me?
Yes, sir.
Yes. I have a question that when we are the bacteria are absorbing the heavy metals. Now, when the treated water is released into water bodies, then whether the water organisms like the fishes will consume the bacteria and will then if human beings consume those fishes, will there be any case of biomagnification, and can it be toxic to us?
No,
That
sir. Before, like the water which is being released into the environment, we will remove this bacteria, and this bacteria can again be recycled for the next batch of the water treatment.
okay, okay, thank you.
That's what I was asking the
We
same
will
question.
remove this bacteria, and then we will send the treated water into the environment.
Thank you, thank you, thank you.
Okay,
Okay,
thanks
sir. Thank you.
for answering all the questions and clarifications. Next, we have
Thank you,
in-person,
sir.
right? Somnath? Yes. In-person. Somnath, এখানে? Somnath কোথায়?
Somnath is our next presentation will be on hemicellulose dissolution. কে আসছে? সব করবো? Okay. I think there is a last minute change, so Jayanta will present, right? Okay. This will be very interesting topic that Jayanta De, he is from first ruler, come MA, come now Wood Group. He is from UK office of Wood Group. He is from this department. তুমি একটু ইয়ারটা বলবে? He is from 97 batch and he is doing some exciting work. That is a talk of the town today, not only town, the whole world. Decarbonization process and what they are doing on the study wise. It will be very interesting because as you know, the whole thing was discussion yesterday was the sustainability. Sustainability meaning that what we have to hold on to that. So what we had was like 25 years ago, it was 330 ppm of carbon dioxide. Now it is 429 actually, this year's measurement. So that is increasing. So it has got the replicative effect. The greenhouse gases, temperature is increasing. Like today, if you see that way, places like temperature, extreme temperature is going on. In July, my town actually in Houston, it was almost at the break point of the total energy consumption. It was like within 0.6%. So you can see the effect is coming. So what Jayanta is going to present on the decarbonization. This is very vital topic. If you can, and any of you or any of us can come with a very economical solution, it will be like the grand success for the whole world is looking for this one. So let us listen to him. We'll have a lot of questions, and then after that, Somnath's presentation will be there. Okay, Somnath, all yours. এখানে এসো। এই কিবোর্ড কাজ করবে? এই কিবোর্ড কাজ করবে কিবোর্ড? সাইডটা কত চেক করতে পারেন আমি?
नहीं हो रहा है क्या?
ওখান থেকে
वहाँ पे पावर है क्या? ठीक है तो है। হচ্ছে না তো? কিবোর্ডে হচ্ছে না কেন তোমার? এটাও তো হচ্ছে না। স্লাইড বোর্ডে নেই কোথায় ওই জন্য হচ্ছে না।
that's fine, that's fine. এটাতে কাজ করছে কি? ওটাতে কাজ করছে কি? ছোট ওয়্যারলেস কত ওখানে লাগানো আছে? মাউসটা কই রে? স্লাইড মোডে নিতে পারলে যে প্রবলেমটা আছে ওটা ঢুকে যাচ্ছে ভিতরে। ঠিক আছে ঠিক আছে, আমি দ্যাটস ফাইন, আমি তাহলে এইটা হ্যাঁ জাস্ট ক্লিক করলেই হবে। ফাইন ফাইন ফাইন, আল ডু দ্যাট, আল ডু দ্যাট।
Good morning, everybody.
এটার মাইক আছে, কাজ করছে না? মাইক কাজ করছে না মনে হয়।
Can you hear me? Online? Okay. Sorry about the technical glitch. I think slideshow is not working, so that's why I have to just go through one after another. Sorry about that. So I will present on the decarbonization, and as Joyantada said, decarbonization is the topic of this decade, not for the right reason. So we as a chemical engineer, as probably is a theme of this symposium, that we have the power to change. So this is one of the topic, or one of the part of the whole decarbonization. I will show you some of the things which we can do as a chemical engineer when you are going into the industry, or if you are in the industries, you can do something to minimize the global warming by decarbonization. So I'll go through some data which are interesting data to analyze, and then we'll explain what are the overall carbon capture and sequestration technical chain, what are the different parts, and then we'll go through 4 different plants I have chosen which are the major contributor to the global warming and to the CO2 emissions. So it's the power plant, cement plant, refinery, and steel plant. And then Wood has got one methodology, we call it core methodology, where we can help industry to decarbonize the sector. And then some thoughts for all of us that where we can reach. So this map is the CO2 emission map. And as you can see, the total CO2 emissions every year is around 36 to 40 billion tons per year. Is a huge number. And as you can see here, US, China, they are the major contributor. And also we have got Russia, India, Brazil, Australia. They are also take part into this CO2 emissions to the world. And if you go into the sector-wise, as I've shown here, the electricity and heat production, which we all consume electricity, we all need heat. In the Western countries, we need heat. And for that, 25% of the CO2 is coming out from that product. We have all the global industries, which we all use, cement, steel, chemicals. They contribute 21% of the total greenhouse gas emissions. And we have got agriculture, transportation, which is very difficult to decarbonize because they are all small parts, and then bringing them together, it is very difficult. But that's why you will see probably in transportation, we are using now electric car, so that, okay, you can decarbonize at the source and you can get the green electricity. Then the buildings and others, they are 16%. So in today's topic, I will cover this around 50%, 46 to 50% of this sector, where and how we can decarbonize. And this is the theme of last COPs. COP26, COP27 just happened in Egypt. that we have to act now to limit the average global temperature not to go above 1.5 degrees centigrade. And that's for all of us, for the humanity. So if I go into the overall CCS chain, so there are 4 parts. So first, the CO2 which we emit from, as I discussed, either in the power sector or in the different sectors, you have to capture. And then after the capture, what would you do with the CO2? So you have to compress. And then you have to transport, and then you have to store. So these are the 4 parts, and each part has got its own role. And then while we are designing, it has got its own challenges. So how we can overcome, so I will go a little bit of that, but 20 minutes is not enough. So this topic, we can talk for the hours. So first we go into the CO2 capture. So there are few ways you can do CO2 capture. So one is a post-combustion, which in home, when we do the gas ovens, so we produce CO2. So that's the flue gas. So you can capture from there. So in the industrial sector, we will see that, how this flue gas, from the flue gas, you can capture CO2. Pre-combustion, so that means the CO2, the C is now bad word in the world. So you have to take the C out. If you take the C out, then if you can keep only hydrogen or any other molecule which can be combusted and get the energy, that's the way to go for. That's why it's called pre-combustion. I'll go into details. Oxy-combustion is one part of the post-combustion where you can use only oxygen rather than the air, so that you can minimize the volume of the 79% of the nitrogen. Then the compression is the part where we have to be very careful because we need high pressure storage and high pressure compression. And then the transport, either via pipeline or via ship. And then where you store, whether depleted reservoir, saline aquifer, or some for enhanced oil recovery, which people are using. We did one plant in Abu Dhabi called HPAD, so they're using that for UR. And also in Saudi, we have used few. And in Algeria also, people are using that. That plant came in 1990s. So this picture is from North Sea. We are very much into this project. So I was involved in Net Zero Teesside. So we have got few hubs coming. Net Zero Teesside, and then also the Humber. So this is the industrial sector. It's in the northeast of UK. We've got big chemical plants where we can capture, and we're bringing one power plant here in Teesside, which is 500 megawatt power plant, which we design, and that carbon dioxide will be captured from there, and which will be stored in North Sea Endurance 1 of the saline aquifer. So a little bit more on the post-combustion capture. So post-combustion, as I discussed, so the capture of the CO2 is after your combustion has taken place. That means you are already converted to CO2. So it has got a large volume of the flue gas because we have 79% of nitrogen. And this gas has got low pressure because of the flue gas, as you know, it has nearly atmospheric pressure. So you have to capture from the nearly atmospheric pressure. That's why even the partial pressure of the CO2 will be very low. But one good thing about this is that it can be retrofitted to the existing power plant. So this is one of the schematic where the flue gas can be brought into the direct contact cooling, because flue gas temperature, as you know, flue gas temperature is quite high. So in the normal gas turbines, temperature is around 500 to 600 degrees centigrade. But this capture process, it works around, say, 40 to 50 degrees centigrade, or you can go probably maybe 80, but that you have to push. So the large amount of the heat, you have to take it out. So that's why we use a direct contact cooling. So this is just a normal water we circulate, and they take the temperature down. And then we've got a blower, because this is, as I said, is a near atmospheric pressure. So you have to boost the pressure to overcome the pressure drop of the absorber. This is a large blower. So if you see the blowers is like this size, it's 7-8 meter diameter fan on this blowers. It's a huge blower. And then it goes to the absorber. So I've taken a picture from Boundary Dam in Canada. So they were the first one in the coal-based power plant. They introduced this technology. and I know somebody from Shell was here. It is their process, CanSolve. So they developed the actual solvent, and that solvent is actually MEA-based solvent. So any amine-based solvent can work, but this MEA has got attraction of CO2 at the low pressure. So that's why people use MEA. We also can give the guarantees. We do the simulations, and we can use piperazine and MEA. But normally people prefer to go with the licensor, like KBR had something, Fluor has technology, MHI, Mitsubishi has got technology, and Shell has got a technology. Yeah. You have as well, Technip has as well, of course. Yeah, you have got technology. So people use that solvent, and then you can capture CO2. One interesting thing you can see from this picture, this is a tower, it's a column, but it's a rectangular column, which people, when we started this, people couldn't think of a column can be rectangular. Always we think column always will be cylindrical. But you don't need that, because there's such a low pressure. It's a few millibar we are talking about, not even bar. So why do I need that? So rectangular column can work. And it's got huge area for all the internals. I'm talking about 40 to 50,000 meter cubes of area. It's a huge tower. But your regeneration column can be cylindrical, normal cylinder. So that's about the post-combustion capture. The pre-combustion capture, which is, as I talked about earlier, that if you can take the C out, so you capture the CO2 before the combustion had taken place. And good example is your SMR process. So when you convert methane to hydrogen and you go through the SIFT reactor, so this is the high temperature SIFT, low temperature SIFT, and then you can capture the CO2, and then hydrogen you can use as a clean fuel. And that's all about the pre-combustion capture. And the advantage is it has got high partial pressure, so this pressure is quite high, so normal absorption material like amine can easily work. You don't have to go into the extreme. And then some of you probably will be aware of this Allen cycle, where this is to produce the power, but through the pre-combustion route. This is not yet commercialized. This is still in the stage where people can use it, but it's not much popular. Then I'll go into the oxy-combustion CO2 capture, where instead of air, you use nitrogen. So what you have to do, you have to keep the ASU, take the nitrogen out, use the oxygen, so your volumetric flow rate is much less, so you can handle. Because on the post-combustion, if I think about that duct of a normal, say, 500 megawatt plant, 500 megawatt plant will give you 2 mmTPA or 2 metric ton per annum CO2, your duct size will be 7 meter by 7 meter. So it's more than this volume of this room. So a huge duct. And in this case, you can minimize the duct because you don't have to handle that much of nitrogen. Next, come to the compression. So as I said, the compression is the very interesting part for this CO2. So you capture the CO2 at low pressure, and that pressure I'm talking about few bar, 1 bar to 2 bar, and you'll be lucky if you get 1 bar, because that blower is very big blower, so we don't want to go into that much high pressure. And then you want to transport a large amount of the CO2. So how do you transport, and what's the minimum investment process, and where is the break even? So what we do, normally we compress up to 100 to 200 bar. And probably some of you are familiar with this, and of course all the professors, they know about this. Then this diagram of CO2, particularly for the CO2, triple point is at 84 bar, around 80 bar at 50 degrees. And we want to go with the supercritical. We don't want to go here in the gas phase, because gas phase will be huge. And if we want to go into supercritical, it will be liquid density, but the vapor velocity. So handling that CO2 is very, very risky. And if you want to design that pipeline, design the compressor, it is very tricky. Only few companies can do that. It has been commercialized, but the first few stages of the compressor will be compression, and the last stage is a pump. So that's why it's very interesting, and then need to keep in mind that where your CO2 lies and at what pressure you are transporting. And that's why this pipeline, so this is from, I think it's the Drax project, oh no, White Rose. We were involved in the White Rose. So this is the long 100 kilometers pipeline, and think about that 200 bar quasi-liquid is flowing through that, and any rupture, any leak, it's a huge safety concern. And then if you are trying to do the inherent safe design, your thickness of the pipeline will be quite huge. But if you want to design a relief valve, and that will be very tricky, supercritical relief valve. So that's why when we're designing this, you need to make sure that you are in the right phase diagram. And then other important thing is this phase diagram changes based on the contaminants CO2 has. So if CO2 has some methane or some other, this phase diagram, your 0.82 bar will become say 90 bar. So that means you have to be always above that point to be in that supercritical phase. Otherwise it will be gas phase and then it will flash. Storage wise, we have got saline aquifer, and I'll not go into too much into the storage because this is the part of reservoir engineering, it's a different topic. That injection takes place in the deep saline formations, so where normally CO2 goes and stays for the next million years. It will not come out. And same way the oil and gas stays in the reservoir. So what are the key assessment area where you are designing this carbon capture or when the new power plant is coming? And I'm sure in India also, because India has the pledge is after 2050, it should be zero carbon, net zero. So that means any new power plant is coming, if it is the gas-based or coal-based shouldn't be, but if the gas-based, they have to have a carbon capture plant with it. So first you have to see that, okay, which carbon capture process, whether it's post-combustion, pre-combustion or oxy-combustion. Then what's the combustion fuel? Can you change something? So if you are designing for the coal, can you not convert into the natural gas where your emission is less, or biomass, but still you have to have that CO2 capture. Site location, so where the site is. So like here in KTP, Kolkata Thermal Power, so if you want to have a carbon capture plant there, yes, you can capture it, but where do you store? Is there any storage nearby? So that's the challenge for all the power plants, existing power plants. Then the normal chemical engineering principles, all the cooling media, means of transport, what is the physical state which we discussed, whether vapor or dense phase, then the storage type which I have already discussed, and then the sink type. So there is subtle difference what is a storage and sink. Okay, sink onshore or offshore, so that differs based on the geological formation of the earth. So you have to keep all these things in mind when you are designing for the plant and if you want to decarbonize your sector. I'll go a little bit more detail into these 4 plants we talked about. So the power plant, decarbonization of the power plant. So this is the data from 2005 because there's a published data, and I didn't want to give you the recent data because they are not published. So from coal, you have got 7.9 billion. And the natural gas has got 1.5 billion and oil has got 0.9 billion. So these are the CO2 data per year, and these are the number of large point sources. So we have got more than 2,000 sources from the coal, and then say around 2,000 from natural gas, and the coal also is 1,000. So these are the power plant sources where you can actually employ this carbon capture. This is around 5 million metric ton per CO2 per average power plant. So you have got a huge opportunity if you want to do it. Only problem for this type of plant is we have got only, if you use natural gas, you've got 3 to 5% CO2. If you use coal, it's got 12 to 15% of the CO2. But most of the cases, you can use post-combustion. And it has got its own challenges, which I discussed earlier because of the large volume and the low concentration. And you are familiar with this type of power plant pictures where you can see that these are the stacks where you can use this post-combustion. So this is the plant which we talked about earlier, is a absorption process using amine, and this is the amine tower, the absorption tower, and this is the regen tower. And you can see the duct, and which I was talking about, the duct is a huge duct, this duct. And this is actually the cogen plant. From here, the duct is going into this carbon capture facilities, and the flue duct also coming from here. So it's a huge facilities, and it's a large volume you have to capture and you have to handle. In cement plant is another one where we emit huge amount of the CO2. But good thing is that concentration of the CO2 is quite high, 15 to 30% by volume, and it has got NOx, SOx, so that has got its own problem, and you can actually use SCR for the DROX and then the sulfur bed. But what you can do is a post-combustion CO2 in the kiln, you can use it to capture most of the CO2. The other thing is the cement plant, they use huge amount of the energy. So if you de-link these two, is one for the cement plant where you can't do anything because it is in the inherent process and it will generate CO2 because of the cementing process. But for the power, you can use the blue hydrogen, which we talked about earlier, pre-combustion, which is SMR with CO2 capture, or the green hydrogen, which Avro talked about, that's all the hydrogen sources. So you can get the hydrogen for the green way or the electrolysis way, then this sector can be decarbonized. And if you come to the refinery, is most of the chemical engineers somehow related to the refining industries, whether it's petrochemicals or other byproducts. So we are very much aware of this refinery has got very high CO2 production capacities, and it does, because you need heat, you need power to run a refinery, a big refinery. And the sources, furnaces and boilers, you've got all the utilities, you've got FCC is inherent, you can't do anything because that's a part of the FCC process. You will generate CO2 and the hydrogen production, of course. So all the hydrotreater, hydrocracker, everywhere we need hydrogen. And that hydrogen, if you can do it in the blue hydrogen way, then you can decarbonize this sector. So the post-combustion CO2 has got a big potential here. Refinery, I was working in one of the refinery projects in Humber, and we showed that in the UK. So they are going for some of the boilers and some of the furnaces where we can retrofit the capture plant, and then you can decarbonize part of the refinery, not all, maybe 5%, but 5% is better than nothing. So that's the way you have to start for next 30 years, all the refineries and all the other industries. You have to go and start with the small, and then you can do. This is a picture of Port Talbot Tata plant, which we were doing a study to decarbonize the whole steel plant in Wales. So it has got this sinter plant and blast furnaces. So you know the blast furnace is a big producer of the CO2. And if you just break down the CO2 production of steel industries, 50% of the CO2 comes from the power generation. So again, here's a big opportunity. If you use the blue hydrogen or if you use green hydrogen, that 50% is a low-hanging fruit. You can do that. And Tata is very much committed to that. Whole Wales is a small country, and they are going for even for the house as well. So it's a normal domestic also. There's a hydrogen pipeline coming, and Tata will be part of that. And they're bringing this hydrogen to in a way that we can decarbonize some of the domestic as well. The 27% of the CO2 comes from the blast furnace, where you can retrofit the post-combustion. and in the overall fuel gas system, it's every part of the plant, like center plant, coke ovens, and Bosch, the basic oxygen steel making, they produce the gases which has got CO2 as a different percentages of the CO2, but that you can mix this and then you can put a post combustion. So this is the decarbonization model people can use. So it's a very, very systematic approach where you are, it's like a 3 hours of the like reuse, recycle, this type of things. So you can first substitute the fuel or feedstock, like instead of methane, use hydrogen, if you've got opportunities. But we look at the overall sector. So when all the big plants come to us or the organization come to us, so we look at the different their own product and then where their own product can be used. So like when we were looking at the tea side, we were looking at the whole tea side industries. It's not only the power plant, but we were looking at the CF fertilizer, we were looking at the BOC, their oxygen plant. And then if you bring them together, then the advantage is that you can have only one CO2 pipeline and everybody can fit in. So then one company is not paying for the whole pipeline. And that's the beauty. So this has to be the overall. So, okay, I'm on the last slide. And then you can capture the use of CO2, which we talked about. You can offset by doing the clean. So this is part of the overall. Also, you can reduce by improving the energy efficiency. Of course, if you have got energy efficient plant, you will use the less fuel. And then at the end, evaluate that how you can overall, you can do it in a way so that everybody benefits. So that's our score model. So in the last slide, I just need you to think, what's the path forward? It is a complex undertaking. It is not easy, because if you look at it, look at our city, Calcutta, yes, there's a lot of CO2 emissions happening. What can we do? Okay, all the individual car, can you do anything? Probably not, but if you change it to electric vehicle, yes. But there are lots of different things you can do, small, but overall probably we can achieve. And another thing is that we need to have a technology shift. I think when coal was replaced by oil in 1950s, 60s, people were thinking, oh no, coal is the way, we can't. So that change is required, and change we can bring as a chemical engineer, because when we are designing the plant, we can go back to the client and say, yes, you can do this way. Why not? Think about it. And capturing CO2 as a reasonable cost, that's a very key. So currently, 2 MTPA plant will cost you $1 billion, which you will not get anything back. So that's the thing we need to reduce, then only people will use it. And the deployment of the CCS, the whole chain you have to understand, and you have to understand the sink, understand where you're going, and then we can do it. Thank you very much.
I think this is an excellent topic for the day and very well presented. We are twins, so we are same name, okay? Only separated by time zone, but time and time zone, okay? He's 10 years younger than me, but excellent topics. And as he has shown few things, it is on November, 4th of November, there was a publication that China, instead of giving all this virus and all these things, they are doing the CO2 utilization to make methanol. So that will be reducing carbon dioxide by 5 lakh ton or 5,000 metric ton. So people are doing the work, and he's from this department, I am from this department, and this guy is sitting there, Samuel. They are doing a study as we speak to capture from carbon dioxide was a post combustion, and we are doing that one. And Shell guy is there, right? Is there. Let me tell you something. This MEA is discovered like maybe 60, 70 years ago. We did not find any other alternate to that one. So many of these young bright minds are here. If you find something, shell will take you or you will take shell over very quickly. This is like amazing thing if you see that way. For the students, did you see some of the presentation, the critical point that Partha used to teach us? I remember that one. CO2, when you capture, as he said, there is no return on investment. So it will be coming out from the cost. If you can make something valuable, some return, that will be good. And when it goes, we did a project like for my company when I was there 10 years ago, and we abandoned this one because there was no infrastructure. You need to inject this one 6 kilometers under the surface, for which you need a 7-stage compressor machine, which was not there in the market for this capacity. So we abandoned this whole thing. This Department of Energy, one guy from IIT Kanpur, he was heading the department, so he said there is no infrastructure. Right now it has changed in 10 years' time, because otherwise we cannot make this blue planet surviving. You can see this, all these things. This is very interesting topics. If you guys like any of the, you have any questions by the way online? No? Okay.
At least in Bombay region, there are so many refineries.
Yes.
There are so many things. And Bombay itself is a polluted city. And there are nearby, you can say, Bombay High, as well as Ahmedabad Basin. So why can't we use them for UR or at least?
Yes, that's a very good point. That's a very good point what he suggested, Somnath. UR is the enhanced oil recovery. See, we want money from something in return, like particularly the oil company. So if you can inject that one, the CO2 collection, Singapore is following a model, not only Singapore, the Southeast Asia. There are different plants will be capturing the CO2, and somebody, I think Shell is spearheading that one. You capture and dump it in one place, and they will take it into the sea or some place in Indonesia. Samuel may know better. So whole world is working, not only that what he is doing or we are doing an isolated way. So you can see how this small department that started long ago is trying to solve some world problem or issues in different capacities. Another thing I would like to add with this post-combustion and pre-combustion capture and all, there is another thing called DAC, direct air capture. If you can see that model, Loyndell vessel is installing, I think it's a huge amount of money, not to do anything, just capture the carbon dioxide from air and inject it or do something with that one. Compared to that, say 420 or 430 ppm of carbon dioxide, compared to this one is showing 8 to 10% of carbon dioxide. The point source capture may be a good alternate to this capturing from the air. But let's see which one wins. Any questions, Samuel?
My question is, all these.
Okay, now my question is, all the processes that goes forward, what are the challenges? More especially the brownfield.
Yeah.
Good. Yeah, it's a very good question. The post-combustion challenges, as probably I mentioned, is a volume. It's a huge volume. And you'll have a layout, a fixed layout. So when you are bringing that plant, okay, you need to find a space. And also the ducting from the existing flue gases, and that doesn't have any pressure. So normally it has got a few millibar at the bottom of the stack. So you need to have a blower first, you need to find a space, and then you have to take that flue gas to somewhere if you have got space, and then you have to do that. So that's the first challenge, the infrastructure and the construction of that. And is the existing brownfield, the construction of this huge duct could be very, very challenging. And there is a thermodynamic challenge as well because of the low pressure. So you need to find a solution. So for boundary dam, I think several guys are here. So in the first few years we had a lot of challenges, because if you have got contaminants, that will degrade the solution very, very quickly. And unless and until you start the test plant, you don't know what are the different contaminants. And also for the CO2 compression as well, the contaminants has got a big part to play. So that changes. One is the pressure and also the corrosion. So if you have got CO2 with oxygen, So, and oxygen, I'm talking about few, like Peterhead, you know. So in the Peterhead, we had to do, just did capturing of the oxygen as well. So oxygen removal, you have to bring the oxygen down to ppm level. So it was at 10 ppm level, and anything more than that, it will corrode the pipe. And then if anything happens in the down tubing, it's a very costly affair. So these are the post-combustion. And then pre-combustion has got less challenges than pre-combustion, but retrofitting is very, very difficult. You can't retrofit. Yeah, because no client will tell you, okay, I'll take the plant out for 2 years. Nobody will do that. So you have to bring your modular plant and then just plug in. That's the concept. That's the way you can do. And the post-combustion, that's why it has got a bigger future. Thanks.
Sampath. Hey, guys and girls, you need to ask some questions. Sampath. Microphone also. Online, any questions, you can write it there, or you can just.
I was about to ask what is the status of reverse combustion, and rather than informed that China has done something, and what is the status in the industrial scale? May I know?
Okay, one plant that has started. See what, as of now, the way the methanol is synthesized, it is not from CO2. It goes to CO and then forming methanol. So it is called WRSG. WRW is reverse water gas shift reaction. I do not know how good it is doing, this plant, but I may get some data. So it is a large scale, it is an industrial scale, and Sinopec Engineering, that is another company, guys, they are our competitor, all the young engineers. They're very nice, very good, but they are competitor. They have built the plant. We don't have any data yet. I'm trying to get some data. Getting data is difficult, as you know, from China. But they are doing a lot of fantastic work, by the way. Take us China as the main competition, not. But that is going on. A lot of work is going on. No, this is industrial. You see, hydrocarbon processing, November 4th, this year, 2022, there is an article, full article is there. They are claiming this, they have done it. Scaling up is a problem. See, when you inject CO2 in underground, after it goes for maybe 1 kilometer, it becomes supercritical. We do not have much information how it will behave long term, how it will be doing after this, it becomes supercritical condition, what he was mentioning. And so these things, there are a lot of challenges there. Any question online? Okay, students, did you notice one thing, when it is burning the natural gas and coal, how much carbon dioxide differences is there? You guys have to keep an eye, all these things, so that you can talk in your interview. And when he is interviewing for you people to recruit, so you have to say, I have seen your presentation and this is what it does, So it is very good presentation. Any questions, Parthuda? Parthuda has got a question. Okay. As
of now, is there any commercially viable super experiment process going on?
Yes.
Yes.
Yeah. So the Boundary Dam in Canada, they are injecting in Canada.
How many the things are injecting in the petroleum?
So petroleum EOR is going on last 10-15 years, and only for this, just disposal well, they have started. Cold.
What is the what fraction of energy? If you have power plant, you are generating energy. Now, what fraction of energy is required to do this?
Yes.
This is an excellent question.
Yes. It's around 20%. You have to add. Yeah.
He is going a business talk, but it is around 30%. Samuel, what you are asking, Parthuda, Samuel, they are executing a project for the ethane cracker. I don't know whether I can disclose that one. From the exhaust.
Yes, it's large.
It is little bit larger because you need a lot of steam to regenerate the amine and the carbon capture. You have to cool it down, then you have to use the amine. Amine is again Shell guys, whatever they own the world, and then you have to regenerate.
and send it back, and there will be some reject also.
It's very energy intensive. You have to add that.
So you have to add around 30% of your, suppose you have a huge power plant. Huh?
Yeah, okay.
30, yes. So you have to add that facility, around 25% additional capacity to capture the carbon dioxide.
You can do a lot of energy integration, but as Joseph said, probably on the conservative side, yes, 30%.
What he said actually so true. We had a walk down with Samuel in the plant. It is like 70 feet up. Guys, you need to listen. It's around 70 or maybe 4th story or 5th story top. And you are having a huge duct to carry that. So it is challenging. I think Kaushik was mentioning.
You have to elevate the whole thing, yes.
Lot of things are there. Lot of things going on as a engineering. So you guys have a lot of challenges because we will not be there definitely on the scale. So any questions? Anything? Okay, tumi bolo. Or naamta khub sundar. Ki naamta bollo? Or Onargo.
I am Onargo from Producer. So my question is somewhat linked to Sir's query. So what about the scope 2 CO2 emissions? So whatever we have seen here is scope 1 emissions. Scope 2 is like whenever we are employing a carbon capture technology, we are putting in more energy like
30%.
source or compression source. So are we reviewing like industry whether there is any possibility to recover energy from the system within and utilizing that to be used for compression or to meeting the sources to capture CO2?
Very good question again. So this scope 2, as I said, so one is the CO2 emitting by the industry. And then all the auxiliaries, if you can do in the green way, like all the power, you generate the power with the green energy. So then that means you're part of the scope 2. But what you couldn't do probably at this moment, all the vehicle carrying all the stuff to the plant. So that you can use the electrical vehicle, but that is a difficult one because you have to convince your transporter that, okay, I need only this. So that means whenever we are saying is the green energy is not fully green because there's still a lot of scope 2 where you can't do much. But for one of the plant in Saudi is coming called Neom City. So they are fully green. That means anything you use there, electricity to anything, everything has to be green, either through your hydrogen production through the electrodes, but there also, if you're using the green hydrogen production, that electricity has to be green by the wind power or say nuclear. So the whole thing you have to look at is not only the part. So part will give you probably say 80 to 90% max. So another 10% if you want to do, then you have to look at the scope, the last periphery, and then only you can do the whole thing. Thank you.
Okay, I think it was very interesting topics and discussion and presentation. So thank you very much, Jayanto. If I don't have any questions, we'll have Somnath now. Somnath, one thing is that we are running little late. So, there is a question in the chat box. Okay, what is the question? Chat box question. Okay, that's a philosophical question. See, which one is that? That earthquake may happen or something.
Thanks for the question of that CO2 injection and anything with the earthquake or what's the damage in the geological. So I will ask the same questions. Okay, last say few million years, all the gas and oil was inside. So why earthquake didn't happen everywhere? So it's not earthquake may happen, might not happen. Is the engineering where we are injecting, how we are injecting, how we are keeping the all well capped, and then the reservoir capped so that nothing comes out, and is not a single point discussion or one guy will take the decision. is a joint effort. So we as a chemical engineer always think safety first. So everybody is working for the safer world. So I don't think there is any risk of any earthquake or anything when you're injecting CO2. That can be eliminated. I'm not saying it cannot happen if you do wrongly, but if you do it properly by the competent engineers, competent company, yes, it might not happen and you can eliminate it. You can design for the safe plant.
Okay, thank you, Jayanta. Somnath, you ready? Okay, we'll give you 15 minutes. Quick, huh? এসো তোমার সম্বন্ধে একটুখানি বলো, আমার এখানে কিছু লেখা নেই দেখছি। না না একটুখানি বলো কোন ইয়ার? 97. Somnath is right here in Pune University. Okay, he is in Pune University. Pune is my second best city of the whole world. So he is from my favorite city. He is presenting on the dissolution of hemicellulose. We'll listen to him. I am requesting him to keep maybe 12 to 15 minutes so that we can have more questions, interaction, and then we'll follow. I think you guys are not hungry yet, so all yours.
Thank you. Thank you, Jayanta. So Jayanta is senior to me to two-way in CU, and subsequently I have done my PhD under Dr. B.D. Kulkarni at National Chemical Laboratory, and that time also his legacy and all those were there. So though we have not met physically, so his presence I felt every time. So actually we are Shishya in two with department as well as at NCL. So thank you, Jayanta. It's a pleasure for me to get introduced under you. So I'll keep my ear so that I'll be prompt. So okay, this is a small piece of work. We started working on it. It's nothing but a part of biorefinery. So already we talked about, Jayanta talked about that carbon capture. So we are moving, we have to move towards the green, and in this thought process, we were working on something on biorefinery. So any and every biomass comprises of lignin, the tough nut, and cellulose and hemicellulose. So hemicellulose can be extracted much efficiently, and subsequently it can be utilized in various forms. So without going other cellulose and all those, I am directly focusing on hemicellulose. So alkali or acid, even acid also can be used, but alkali based soiling is good efficient manner, and we can use to extract hemicellulose, and this is shown as a mechanism. So initially all those low molecular weights are getting removed, and subsequently gradually high molecular thing are going. And as Jayanta talked about, chemical engineering is everywhere. Even the high molecular molecules are moving, and that is because of concentration gradient. So those concentration gradient we can trick and place something on that so that it is getting extracted in much efficient manner. So I want to ponder maybe a minute on this particular slide. So if you see, so this is the wheat stream. This is not our slide. This is I have taken from some reference because our SCM pictures are not so great. That's why I thought it's better to give that one. So we targeted sodium hydroxide treated. Why we have targeted sodium hydroxide? This is raw wheat stream, whereas if we use sodium hydroxide, so the thing is that if you can notice, so the overall structure is remaining intact and only hemicellulose is getting extracted. Whereas if you use acid, HCl or H2SO4, those are getting crumbled. So we can use it further for as an insulation material. We can use it, and we are using it as an adsorbent, and some other studies also going on. Because basic purpose of utilization of biorefinery is that as much we can utilize. So if we use NaOH extracted, so the overall structure remains reasonably good, which can be utilized very efficiently for different insulators as well as for adsorption. And sorry, this hemicellulose is not coming. So basically, it's a path of biorefinery. It can produce pentoses and hexoses, normal sugar. Subsequently, it can get converted to different type of hydrolysis, enzymatic fermentations. And finally, we can have, people are looking for fuel definitely, but we can go for sugars and different types of direct usage. And this particular slide is interesting because I want to show that people are thinking for sugars. Subsequently, we can go for biofuel and other commodity products, biomaterial and specialty. The amount will be less, but the value is much high. So biorefineries are not so much viable because of that cost benefit. But if we can able to do something in proper manner, we can get some sugar, some amount of fuel and some specialty chemical like furan and mannitol, and subsequently I will show that even some small work we have targeted to synthesize vitamin A out of it. And if you see that this particular structure is remaining and we are doing bioabsorbent, utilizing it, all type of lead, arsenic, thank you. So this we are utilizing as bioadsorbent. So basic purpose is to utilize it as whole as possible. Now coming to my particular piece of work I want to talk about. This particular paper got published in AICHE by Guan et al. And as a chemical engineer, we are very much fascinated about AICHE. So in January issue, they published a paper and they thought of that it will follow the qth order kinetics, and as a chemical engineer we know qth order, unless it is equal to 1, it will follow this, and they utilize this particular thing. And subsequently they have done some regression analysis and they are quoting that order of the reaction is 11th order, and it is definitely related to hydroxyl concentration as well as water, and those are related almost 10-10. So altogether it becomes almost 30th order. So as a chemical engineer, I want to ask this particular thing. So is it really feasible to have 11th order with respect to only hemicellulose, subsequently that hydroxyl and water? So that was my real query. And the same year I put a note on AICHE questioning that, and the pattern was showing almost it looks like a linear first order. And I'm fortunate my comment was also acknowledged, and later even this year only Guan et al. Have published some paper where they said that mass transfers and all those are there, but overall it's first order. So I have targeted a simple first order equation out of it. And simple first order equation, and let me come to next. Sorry, it is not visible, so let me, yeah. So now I understood why Joyanta has taken that mode. So this is some published literature data. I have taken it from Yoon et al., very recent paper. So people have worked on that and they got some activation energy, and very few pre-exponential factors are available, and I have tabulated those. And initially I was doing some sort of optimizer. Initially I targeted with multivariable neutron adsorption. Subsequently we have targeted so many things that we have targeted genetic algorithm, but all of that are giving to different type of solutions. And but for different type of solutions means different values of rate, pre-exponential factor and activation energy. All of them are leading to different minima. So that was a real year to me. And then this particular thing for last couple of months, I am working on Bayesian optimization. And in this, I am getting almost all the three together. So I'll be focusing maybe 5 minutes on that Bayesian optimization. It's a new, very new optimization technique, and a very recent book has been available, and this website is given. It is free to download. So and hats off to Professor P. Ray for taking me to this type of thing, that at least though we are chemical engineer, but mathematics is very much important, whatever. So final thing is biorefinery, but if we know maths better, it will really help us. So it was really my question that different values of K, it is 10 raised to 8, 10 raised to 11, 10 raised to 18. For all of them, the fitting is fairly perfect. I can able to fit for all of them, it is fairly perfect. And can I get only 3 or more than that? So the Bayesian optimization is dealing with this, so we do not know the unknown function. Why I am telling unknown function? Because I do not know what will be the K0 and E. So, but we have some data. We have data available from that Guan literature, and there are so many literature data are available. So our target is to develop some function based on that available data. And step is like this: start with some minimum number of data points and try to develop a surrogate function. I'll show in next slide. And then definitely those data points is limited. We need to update our surrogate function using another thing, acquisition function, and we'll keep on continuing until and unless we get surrogate function do not change. And variance means always there will be some variation with the actual result and predicted result. So the variation will try to get it minimized. And how many data points we have, so we'll try to get the best function out of all the data point. So here is the slide where you can see. So the black one is the actual function which we try to fit, and with very much limited, only with 7 data point we are trying to fit some function. Obviously it is not fitting well, and then we keep on iterating, and we can see that even the new point is also getting fitted, so it is keeping that same function. Now as we keep on increasing, gradually we can notice that as the number of data points is increasing, this is trying to fit reasonably well, and as iteration keep on increasing, the function is fitting better and better. We are keep on doing, and so in 12th iteration, please try to figure out that only with 18 data points we can almost able to capture the trend. And with almost 23 data points, we can able to pick up the entire trend. So this is just a sample set of 50 data points. We have not consumed all the 50 data points because it is we cannot have all the data points available for hemicellulosic or any dissolution. So always we'll do with minimum data set. So with minimum data set, so out of 50, only 23 data points, less than half, can able to fit my expression. So presently I have targeted this to figure out that these values, and I can get that multi-Pareto optimal all the points together. But subsequent my trial is going on, because here I have fixed my power as a first order, and I have done a small trial, and in that I have not given any power. Instead I have considered this as Q. And in that, the Q came to be 0.987. In that trial, it came out at 0.987, but that is still some modification are needed, that's why I am not showing it. And 0.987 is also close to this proximity. But this is a very striking feature, that we can have a Pareto multiple number of points. Now this is how it is getting implemented. So the maybe a minute or so in the mathematics behind it. So we have the data points available. All these data points are nothing but based on there are a number of variables based on which those functions, and we are assuming we have sufficient data points so that data is normally distributed, and this is standard probability density function, and overall mean is mu. And covariance is also Gaussian separate. This is nothing but Gaussian kernel. And the conditional probability, and again Professor P. Ray taken us to that probability distribution in our 3rd year. So conditional probability, so we are targeting to figure out the function with this. This is nothing but a vector of the data points available. We know what is the final concentration of hemicellulose that is available, and this is our target. So this can be a Gaussian estimation, and after some modification we can able to get it a normal distribution like this, where mu and sigma square are nothing but the mean and variance. And in this case there are two things, that C is the covariance and C tilde is another covariance, and where K is the kernel function we talked about in last slide. So a bit maths, but the standard thing is available, even it is available in presently the in MATLAB also I have seen it is available. So the major another important point is that how to add the new points, because initially with very limited number of data points it is not picking up, we need to add new points, but the addition of new points is done smartly. So that is done by using surrogate function. So initially we loop all the sample variable, and subsequently we build K and F vectors using kernel, and then build C and C delta, we talked about C and C tilde. And then as we keep on changing, the function is keep on changing, so obviously its mean and variance are keep on changing. The variance was there, variance becomes less. So that is keep on changing, and we should keep them tracked. And finally, what is the ultimate value that we are getting? When we will stop, we should stop because of these three things. So number one, that overall surrogate function do not change. So we are seeing that it is keep on changing, and subsequently it is almost matching the same. Or all the data points are exhausted and variation between below threshold. The variance is more, but gradually variance is becoming less. So that is the thing. And in this case, we can use upper confidence bound, because we have provided a particular bound, so that when we are adding new points, the smartness is that we should add new points where the variance is more, and in that case we should try and minimize the the eta is because that requires some sort of optimization thing, because eta is some coefficient which we need to tune, so that initially during this point I need to provide eta more, so that I try to reduce my variance. But whereas in this particular case, when it is predicting very well, that time I will not focus more on this eta. So that type of tuning can be done. And the final result is like this. So we can able to fit. So dot values are nothing but the experimental values, and the simple first order model can able to fit the value even at 10 degrees centigrade, 25 degrees centigrade and 40 degrees centigrade. All the experimental data are from Guan et al. And then we have extended it for some other paper, and we can able to see even those cases also can be predicted pretty well. But definitely there are some point of concern in the initial phase. The same was with Guan et al. Also. At initial phase there are some sort of difficulty, which really indicates there might be some mass transfer effects, because subsequently after a long time everything is leached out, but definitely some mass transfer limitations are there in initial phase. So that need to be tackled. But if we increase the temperature at very high, maybe 150 and 170 degrees centigrade, we have taken data from this. That time even at low temperature also this is doing pretty well, because temperatures are high, so mass transfer is not that much limited, and it is faring reasonably well. So the xylose and glucose, whatever we have obtained, that we are targeting to get some vitamin C by using biochemical route, and actually that will help us to have the biorefinery in more sustainable manner. So if we can able to get it in reasonable quantity, definitely it can be doable. And actually paper from Nature Communication also indicated they obtained a route, and it is but please understand this is only at very large scale. So biorefinery has a good prospect. We need to do some take some data from literature, also from our experiments, and finally there is a good scope. It can be utilized in various several points, and so that's end. So what I want to say is that whatever we can do, that can be a small part of the overall integral part. So it's a overall biorefinery, but if we can able to extract hemicellulose in proper manner, we can able to extract maximum, and the beauty is that if we can able to remain that structure intact, so it can be used as an insulator and other type of commodity. That's all for from my side, and I think I have crossed time a bit. So thank you.
Let's see if we have some questions. I think the word, okay, you will have a question, so please come here. I think one time, this is long ago, not long before you guys, Octave Levenspiel, the kinetic books, he said, give me 10 parameters, I can fit an elephant. Any parameter, like free 10 parameters, I can fit an elephant with any data. So the 11 order reaction, that is like amazing, and what they have done with the first order or close to first order, I think that is a very good word. I want to add one more thing with the wheat straw and the rice straw that we have. If you know, in places like in Haryana, they burn this one and make Delhi almost like fog and smog and all. There is another country, two countries, Samuel is very familiar with that one. In Indonesia, when they need money, they will burn this one. So the smoke will come to Singapore, and Singapore government will say, stop that one. They say, give us money because we don't have money. I have experienced 3 days, they close everything. School are closed, everything is closed. So much smoke. They are habituated with the mask long ago. Like 5 years ago, I was there. So this is a very interesting thing that you guys are doing. So maybe some experimental data will be very helpful. Any question online? Can you check? তুমি কোশ্চেনটা বলো কোথায় গেলে তুমি বলো ক্যান ইউ হিয়ার
See, this is basically, I have used it for parameter fitting, okay. So that for even first order model, simple thing is that pre-exponential factor, RNS, pre-exponential and activation energy. Because my idea was that I have activation energy at 10 raised to 11, sometimes 10 raised to 15. Or both are correct, or one is correct, another is wrong. So that's why, because genetic algorithm has a thing, it can able to get all the different, if there are multiple number of roots. So generally we are accustomed, equation has a single root, but it has multiple number of roots. So all multiple number of roots are possible. And actually by available literature data, we have seen that all of these are giving reasonably good fit. So at least at this present point, we can say that is okay with. So that is the purpose, and Bayesian is trying to give me in one go, I can able to get all those multiple number of, multiple solutions I can see. Okay. And subsequently another thing is I am going for Bayesian because initially I have fixed it first order, but subsequently my order is also not known. So I have given qth order, and it has given me 0.987 as the Q. So which is pretty close towards
first order.
So that is also another thing.
One clarification for me. When you are fitting more, is it not overfitting the data? Like force fitting the data? Or?
Yes, sir, that is here, but here I am providing only a basket. I am not
giving
going for going for like not all the data. I am giving minimum, try to get it.
Okay.
Some more. So how and when I am getting the overall trend is picked up. So I am stopping. Okay. So with the minimum number of data, how I can do it?
Any questions in house here? Anybody? Okay, no questions. Then no questions online. I think this is the last for this session, right? Or one more. So we'll
another session.
we have to formally close it. I think everybody ate so much that অসীমেশন কি বলতে হবে বলো তো আমি শেষ করব Okay, thank you very much for all the speakers that you could come and give a very exciting presentation, and thank you to all the students that you could drag out of the bed and come here to join us Saturday morning. So thank you very much, and you guys will be doing excellent in the future. So with that, all the speakers, কিছু বলতে হবে? এটাই তো আমি দেখি তুমি বলো।
Yes, sir. We are running late actually. Not only late, it is actually nearly, it is coming to our closing session actually as per time. So now we will proceed to concluding session of this symposium. So I would like to request all the session chairs to come onto the dais for discussion. So Professor Partha Sharathi Rai, Professor Parameshwar De. Yes, we have session chair. Mr. Sujit Kanti Roy, Dr. Jayanto Bandyopadhyay is here. He will be here also. Dr. Shobhan Ghosh, he is online. Mr. Kingshuk Bandyopadhyay, and only Basudev Sarkar is not here. Professor Taposh Kumar Mandal, I think he is also not here. And there will be one of our alumni. He is Shobhik De, Dr. Shobhik De. He is currently a researcher in Shell Global Research. It is currently based in Bangalore, India. Shobhik has passed from our department. He did his BTech in 2009 and then MTech from IITB in 2011. After a brief period in Novartis, he left for PhD in Netherlands. Now his research topic was multiphase flow through porous media. Shobhik has already published more than 20 papers in peer-reviewed journals, and he is also recipient of G Global Research Award, Dow Talent Award. He also received an award from American Physical Society, and presently he is a reviewer also in many international journals, peer-reviewed journals. So, okay, Shobhik is there. So, sir, only my request is you please conclude this session within short time. Okay, thank you. Sir, you can take also from here.
So you have had a joint of Bandyopadhyay just now for the last 2 hours. I am now ready to allow Jayanto at the moment to say anything. I would like to hear from Shobhik De what he wants to say to the audience, particularly these students of the university. Shobhik.
can play a pretty important role. I will talk a bit about very small that how, just for example, if you think of a chemical acid, how you can make it circle, right? I'm just going to talk a bit. I think there were presentations today also where it has been told how decarbonization can be done in refineries. So I'm going to talk a bit on chemical acids and
make circular acid. So if you think of a today's acid, chemical acid, you can think of a plant. So when you think of today's acid, you have to realize that a lot of things we burn coal, natural gas, as well as a lot of these make CO2. If you burn these of one non-carbon
feedstock. That's hydrogen or that's electrification. These are sort of couple of ways which we can give green electricity to the assets. Now, whenever you start from there, we have to go to the upstream of asset. That's where this energy comes from. So then you have to think of renewable grids. A renewable grid means either it's coming from wind, solar, or maybe other ways like photovoltaics for solar as well as some grey electricity from the normal grid. If the electricity is made green, then obviously when this electricity goes to reactor of acid, for example, we can recovery SMR is a process of making hydrogen. Now SMR intensively is a process where it needs heat, right, as well as ethane cracking, steam cracking. So if you can use hydrogen or green electricity, then these assets or these reactors can be made much more carbon negative, right? In nature. Then the second thing is the product that's coming from here. Let's see, from steam cracker and flame gets produced, right? From ethylene you make out of products. PET and everything is a final product of these chemical assets. Now then you have to think of circularity, that how using this you can make something like a pyrolysis oil, and that pyro oil can be used to run a cracker. So if those are done, then only you are taking a carbon, you are using it in the asset, and you are again giving it back to the system, and then you can have more or less a zero carbon, right? That's the whole idea of a circularity. We talk a lot of about scope 1 emissions. There's a nice question about scope 2. We have to think about scope 1, scope 2, and scope 3. All these emissions, and that's why I think circularity in that way can be a real success. A bit more how academic can play a very important role. In all these topics, there are excellent R&D spaces or research spaces, right? Academics are working very closely in multiple of them. I talk hydrogen is the source. Currently, hydrogen is made by SMR. Blue hydrogen or green hydrogen are things we are starting to talk. So in green hydrogen, let's see electrolyzers, alkaline electrolyzer, same electrolyzer, SOFC, right? There are multiple others. So those are very interesting technologies that if you want to make 1 cent per kilowatt hour of electricity, that's the typical ballpark of LPG positives, how this can be, like the technologies of these can be developed. So that is one idea there. Materials, we talked about materials. One thing we need to think is the research topic very interesting is, let's see, we talked about computational, right, or digital edge. So why can't we make materials which are much more not carbon based in nature, or actually they can sustain or they can absorb CO2, those kind of materials. So research topic in AI for materials are pretty hot topic in current. So those are very interesting topic as a whole. CO2 as a whole is also very interesting because we are talking about CCUS, carbon capture utilization and storage. And in CCUS as a whole, the technology to mature is very interesting. We use, let's see, saline reservoirs, that's one way to capture CO2. We talked about that. The direct air capture, these all technologies are very nascent stage. And there are plenty of opportunities in R&D to develop that space as a whole, right?
And finally, we also have to think, we had a lot of talk about CO2 intensive technology, but to make a circular economy, you have to think of supply chain. So for example, if you make LNG in one part of the world and if you transport it somewhere, or if you use an aeroplane for the fuel, you have to think of SAFs, sustainable aviation fuels, which comes from a green source. And also very similarly, how many can be decarbonized as a whole. So there are pretty interesting and niche R&D topics which will be able to help us to let's say have a green and sustainable future. So that's a bit from my end. Thank you.
Thank you for sharing students in specific. I'd like to know the feedback from the audience. Here we have the last 2.5 days, comment, many thoughts. Please.
So,
Very important.
so in case, so I am David, 2008 batch. So I came late, sorry for that, but did anyone talk about the battery, next generation battery? Shobik? Okay, so I would like to have brief about that. What could be the next generation of battery? Because when we are talking about carbon neutrality or towards, then battery is the way to go. But the challenge India today have is, or the world other than China, is that we don't have lithium. So we need some alternative of lithium. So right now, the goal for like I'm in academia, so our goal is we are trying to develop sort of material sodium-based electrode. So that is one very challenging topic, because you have lot of sodium with you, like whole C is there, and we can get it. But the problem with the sodium is the capacity of the battery will be lower. So that is very challenging. Like we need to develop a kind of material which can give us the electrode or mobility of the sodium ions inside the electrode, as well as it needs to be like a new electrolyte. So that is the one challenge in this field. And of course, there are sulfur batteries, aluminum batteries are there. So sulfur battery again is promising, but the reusability is the issue. Like the number of cycles you can use it with charging and discharging. And similar case is with the aluminum battery also. So there is, because aluminum is Al3 plus, so 3 times of charge can be transferred, but it is not a reversible process. So this is the area where we as academicians are working. And I will add a little bit with Shobik that regarding the hydrogen, what is the status? Like one of my colleagues is also working with some industry. I don't know exactly which are the companies, but he had developed kind of, it's a simple reforming reaction where he is getting the hydrogen and then a membrane separation for the hydrogen, and almost 19, like what is the purity scale which he reported is 99.999. So that is the purity level he could able to achieve. And yes, so that is one really great, but probably production of that in the industrial scale is again still to be done. So yes, so that is what I would like to see. And as a student, I would say that like those students who are sitting here, and also like new professional, like yes, we can call me, so we are the new professionals, right? We got the new chairs. For students, I would say that if you invest your maybe next, you can think about 5 to 8 years, then this battery technology will can drive you 30 years. So that is by end of maybe 2050, everything will be batteries, right? So that's the goal, and it's all over the world. So and we are Indian, like we have a very new population, like young population, and you are the probably the creamiest of that population. So think about it, that this is a domain where you can invest your life. Okay? Yes.
It is so important right now. I think I had talked with someone the other day. EV, existing EV, the moment you are putting in the new car, you have to have the mileage, like you want to 300 kilometers, right? The 0 mile that you are driving, at the time it is producing 1 lakh kilometer of the car after driving, the same amount of carbon dioxide is produced before even starting 1 kilometer. Meaning, to extract the mine and to process and to make the EV, the amount of carbon dioxide that you are making is more than 1 lakh miles of the car. So, what he is suggesting is instead of lithium, if you can do something, it will change the world. Absolutely. That's just one thing I cannot show. Okay.
Yeah. So, thank you.
আচ্ছা এরপরে কিন্তু ইন্টারেস্টিং সেশনটা আছে লাঞ্চের পরে আবার ডিসকাশন
I want some of the students to come up. Some of the students please come up. এক দুই তিন চারটায় চলে যায় একজন ওখান থেকে বলতে যাওয়ার পর সে আদেশ স্টুডেন্ট বলছে কাকে ধরেছেন এই যে কেউ একটা উঠে এসো রেহাই নেই এই তোমার পিছনে কে বসে আছে রাস্তা কে দাও তোমার ঠিক পিছনে তোমার ঠিক পিছনে সামনেই বলতে হবে একদম পেছনে নীল জামা উঠে এসো আর নীল জামা আছে সেই আপনি সবগুলো মেয়েদের ডাক্তারি
No, we need empowerment. We need women empowerment.
হ্যাঁ আজকে প্রথমবার হয়ে গেল শেষ
Now we are dividing into two things. One is tell us what do you feel about this symposium, number one. And number two, you are supposed to ask us additional questions. We will immediate at this start, we try to avoid because we can't answer that because you don't know that. So these are the two jobs you are going to do. First you have to tell us what you have done and whether you think it is of any use to us. What you really think. Not that
এই তোমরা শব্দ কম করো তোমাদের টাইমিংটা একটু ভালো না অন করা আছে মুখের কাছে নিয়ে বল সামনে সাজানো না এখানে এখানে সাউন্ড বানাচ্ছে তো মুখের কাছে নিয়ে নে মুখের কাছে ধর হ্যাঁ হ্যাঁ ঠিক আছে হ্যাঁ
I attended almost all the sessions yesterday. I have read And what I feel personally is that the symposium is really great. Actually, I was just listening all of the lectures in your news, and what I feel personally is that I am getting some information about the future. But I am actually discussing with my parents when I'm home and all my classmates and my juniors and seniors that this kind of scenario is going to happen. Maybe we have to be more responsible about all these carbon emissions and these hydrogen emissions and about the energy crisis we are just going to face in 2050. So we just have to be more responsible and think about the future. Not only the present and we are using lots of energy and electricity. So we should cut out the energy consumption we are using every day. That is not necessary. Okay, and we should save as much as we can. We should save, and then we should try to generate something new and see something new. That would be great for us because we are Indians and this is a huge population here. So if we all can save at least a little bit, but it will give us at least 4 5 years or more. I don't know that exactly. But we just have to save at first, and then we have to generate and think about the future. So we all have to be more responsible and quiet to about after taking the symposium.
Good afternoon, everyone. Good afternoon, everyone. I have attended. Good afternoon, everyone. I have attended almost all the sessions. Not, I do not attend many of them, but most of them I have covered. So from all these sessions, I can say that this symposium has really helped us to work and think about the better goal. Yeah. So from the perspective of environment and from different, yeah, it's basically what I say is it's a mediator between the industrial, research and academia, and it's a bridge. I must say it's a bridge between the industry and the academia and what I took back from here is that whatever we are doing, we should think of a larger goal to, meet up. Right from the wastewater treatment, because circular economy is really a emerging topic, and we should think about it. And reduction of carbon emission and thinking of alternative sources of energy. So we should come up with many ideas that we can meet up all these challenges for the environment as a whole, the challenges for humankind, and I personally feel more and more students should come up for research field to with the ideas, emerging new ideas, because everyone has a lot of potential and they should utilize that, and they should come up with new ideas to solve all these problems. And all the speakers actually helped us to motivate for for research work and to think about the real challenges of the society rather than thinking of very petty issues. These are the things. And another thing I want to say is more and more biological researchers should biological aspects, because COVID-19, as we all know, is a very challenging thing. So we should come up with the biological. There are so many researches are going on worldwide, but biological researchers are, research on biological things should come up more. So that's all. Thank you so much.
here. I'm a very new student here because I'm a BTech student and I really don't know very much about this genre, but through this symposium, I can say that all my friends who are from totally BTech, they really grew their interest in this genre and we have come to know about all the problems in the industry. And I think my friends and all the new students who are doing this course, they will grow their interest and solve the problem which industry is facing, and we will surely solve the problem and yes, I can say that this symposium is really very good and it has grown my interest in this field. So thank you so much. You're from second year? Sorry. I'm a BSc, so I really didn't know about this field very much. I just come only 1 year, so thank you.
Good afternoon, everyone. To this series, I am very thankful to all the speakers because in the 2 days, through these 2 days, we get many ideas. Whatever we have to learn in the next year or the next few decades. But in this last session, Sir told us about the EV, which I most interested and thankful, and moreover, I am gets motivated to see all the alumni now where they are. So thank you.
এই সম্বন্ধে পাওয়া যাবে সম্বন্ধে আসি তো অনলাইনে আছে
I can hear, but your audibility is so poor, so that's why I refrain from participating in the discussion. So that is the problem. I am hearing all the thing, but the audibility is so poor, so I cannot contribute from my side. So that is why I prefer to keep quiet and observe it. Thank you.
Okay. So I will now ask Insuk to say something. And you are future organizers. I jumped in as a chair and I just it was not planned, but I'm happy to be here and extremely fortunate to hold the session and the chairing session. The circular economy, when we talk about, there are a lot of symposiums, a lot of seminars, a lot of talks, a lot of papers everywhere. We had almost half the session here. A lot of topics have been discussed. Many we understood, many we didn't. It doesn't matter whether we understood everything or not. But what made me extremely glad and satisfied is that the young lady, yes, that lady, yeah, you, when you talked over here and you told your paper, the circular economy is not something to be discussed in the conference room. It's not just some intellectual gymnastics, There has to be some takeaway. And her takeaway is what more I can do. And it all starts from our individuality. When the first time I was, doing some international conference, there were not conference, a meeting. There were Europeans who came to India. I was also part of that. They were given a bottle of water, and we also given a bottle of water with a typical Indian style, drinking like this. And they were looking at us, hey, how can you do that? It's something amazing. You're talking about it. How do you possibly you're not getting choked? And they are all touching. each and every bottle we turn out. The one only answer which I had, that we learn from our childhood how to share. Even if it is abundant, India is not a country where water is scarcity. We have a lot of water, and no problem with us. We can even digest any quality of water, which you cannot. We have a good immune system, don't worry. But still, we know how to share. This is the crux of the story. When we are talking about circular economy, it is not for this generation. We can manage our economy quite well. But I think many of you have seen an advertisement from Tata Group. In the parents-teacher meeting, the organizer, they asked the parents to draw some picture. And later on, they asked the kids to draw some picture. And the difference was, all the kids' picture, whatever they have drawn, it was only black and white. Because all the colors were exhausted by the parents. It's a great message that today, the way we are extracting the resources from this planet, whether our kids will be able to do, will be able to enjoy anything. We are destroying the air, destroying the water, destroying the soil. What will be their purpose of living? So I really congratulate you and thank you. That makes this symposium absolutely successful. That the students are coming up, they're coming up with this kind of thoughts that what more I can do. Thank you.
Thank you, teacher. Now, as you know, as we have seen yesterday, that the organizing committee consists of Professor P.J., Sujit Kansiri, Jayanta Bandabhadra, and Mr. Chinna. So, three of them are here. So, what was their expectation when they started to have this seminar, and what they have achieved in terms of dissemination of knowledge of the benefit of the current student and the regular awareness. Please, Sujit.
Thank you everybody for participating in these 3 days of symposium. In fact, I was involved in the symposium from the very beginning, right from selecting the theme for the symposium. And now at the end of the sessions, I really feel very satisfied that we have so many topics and so much of discussions, which is very useful and which have been very appropriate to the theme of the symposium, circular economy on sustainable basis and the role of chemical engineers. And we have got so many experienced alumni and the discussions, participations by the members of the alumni and the students really make the symposium very useful. And we look forward to have this type of symposiums every year. And I also encourage the students to participate as much as possible, particularly during question and answer sessions, so that they can participate, they can put forward their questions and clarify things which will help them in their future prospects in the respective research fields and all. I really thank everybody. Thank you, Bhadrada, Bhavishya, Janaka, and everybody. Thank you.
Thank you very much.
আমাদের একটা কথা বলতে সেমিনার that you will give your feedback as part of the session. But when we are sitting in the front and some presentation is going on, you know, Sujita passed out from this department when I just started working, he is opening doors saying that how this thing is done. That's the curious mind. You know, he has retired long ago and all things, say, let it go. So he is also learning that interesting part. I don't have much to say. After lunch we'll have this.
Say of the whole episode. I love to talk about everything, but we have been interactive session, academic development, etc. If we are taking about the industrial need and industry institute introduction, etc. I am happy to inform that during last 2 days, what we delivered in Apple, out of that, Belgium
who has come from God pattern, he is getting some time out of the brilliance over here. And he refused to remember that he can become a BCC as well. So now I will hand over for his comment and declaration of the next symposium.
Before that, I will make a different statement than our President, Professor. We have talked about what is it, meeting or something like that. That is something I have vociferously objected to. It's not a committee, it's the whole alumni association that is doing it, and there is nobody in charge of, separately, specifically in charge of this thing as a, what would I say, as a chairman of committee or so. So please don't say that there is a seminar committee or symposium committee. It is done by the entire department. And one of the reasons I want to avoid that is that we have, if you look at us over here, we are old. I don't know about Joyanto or today, but we are old, we are fairly bloated, I would say. Self-serving people, and we always want egotists. We always want that we will be keeping on talking and everybody will be listening and saying, yes sir, what you have said is very fine and nice. And that is something we have got to avoid, and that's why I want the students to come up. They should come up, they should be able to ask questions, and they should be able to say, to hell with your ideas, this is what we think, this is what we are going to do. It is for the younger people to come up with new ideas. It is for the younger people to replace us effectively, and let us not be in charge driving the rest of the world. It should come up from you. About the symposium, all I want to say is that you should consider this symposium of the department, alumni, and only thing I want you to do now, one thing about it, is that this thing should go on as long as the department survives. You will long after we are dead and forgotten. We want that. I hope you can transmit this thing as you grow up to the younger and younger generation, and that this thing continues. No matter at what level. I do not believe in starting something with a bang and then fizzling out. Let's start something which is small initially and let that keep on growing, and let that grow into a very large river, and will be going out into a very large reservoir of knowledge and understanding. So I don't want too much of marks and festivities to be associated with this. That's my idea was that it should be more concentrated on knowledge, more concentrated on understanding and friendship. I wanted to make this thing inclusive. Anybody who has anything to say should be able to present his or her works over here. In fact, I remember saying to Jyoti, she is now the, I think, PIL ED or something. ED. Executive Director. But she has a troupe of singers. She goes around and does performance and things like that. Even when she is in charge of a department like that. And when she said that we don't do anything academic or so, how are we going to present something? I told her that even if you give a lecture on the
history of presentation of Rabindranath Sangeet, even that will accept and publish. Anything that you think what communicating, anything that you are doing, you should be able to give over that. We don't want that in this seminar everything is going to be a EICSE journal or the paper. We are going to publish that. We are on online or on soft copies. We can always divide sections which are of chemical engineering, which are of fundamental values, or which are journal work publications. We will also take other sections where other types of things are included. Now, this is what is my opinion. It doesn't mean that everybody has to follow this. Whatever will be the general opinion of all you people later on, the symposium will follow that. That's not my idea. So, I have given out my ideas. Only thing I would like to you to continue is that this thing should go on as long as the department lives, long after we are all dead and forgotten. Thank you.
Particular for you and all the teachers, we are not voting and voting. We respect you for your knowledge, care you show, and the sincerity. Even after 30 years or 40 years from coming to the discipline, we still talk about you because you do care about us. That all the students are talking about. Another thing that I would like to say, Fatima, there are some things that we always want somebody should be there. What Fatima is telling, no department, no discipline, there should be no person. That is an anthology approach in management. It did not work that way. You can do the studies, I will not say much. We need to have one person and we consider him and or she to be there so that you can come and say, hey, this thing is not working. Suppose I was giving feedback, a lot of rice is getting wasted. Example was telling. So I have to tell somebody, right? With that, it is not voting and voting you. We do respect, honor, and we are good health.
After that, next is the both are the right fitting work, befitting work for strategy. In English, it doesn't matter. It's not respect. It's respect is superficial. Shraddha is something big, coming from very deep. It's very happy.
And execution.
Next year, we can do it about approximately around the same time. This year it was 22, 23, 24. Next year it will be 21, 22, 23. That will be Thursday, Friday, Saturday, just prior to Christmas. Tentatively that, because it may require some changes depending on situations later on.
New executive committee has to, but tentatively, what Dr. has said, we will follow that. So with this, I declare the annual symposium 2022. Thank you. Nothing like giving 35 minutes for lunch. Today we are prepared that. So I will request all of you to finish it by half an hour and come back here by 2:30. Please, students, students have